Have you ever wondered why the planet Mercury, the smallest and innermost planet in our solar system, doesn't exactly follow the path we expect it to? It's a curious case of celestial mechanics that has had astronomers scratching their heads for centuries. Mercury follows an elliptical path around the Sun, but this ellipse isn't fixed. It gradually rotates, causing the point of Mercury's closest approach to the Sun, or the perihelion, to shift, or precess, about 0.001 degrees per century. This isn't what we'd expect, according to Sir Isaac Newton's theory of gravity. Newton's theory holds that any two massive bodies attract each other. If we apply this to Mercury's movement, we must consider not just the Sun, but other celestial bodies close to Mercury. After all, while the Sun is the primary influencer, other planets do exert a non-negligible effect. So we calculate these small perturbations, expecting them to account for Mercury's orbital precession, but there's a snag. Our calculations for Mercury's precession rate are 7% off from the actual measured value. A discrepancy too large and consistent to dismiss. So what are we missing? Einstein offered a radical solution to the problem. Rather than considering space as a void in which masses float, he proposed that space and mass are intrinsically linked. In his general theory of relativity, Einstein suggested that a mass, like a star or a planet, doesn't merely exist in space, it shapes it. It warps or curves the space around it, and a mass experiencing the pull of gravity is simply following a path in this curved space. Consider this: a star warps space in the same way a heavy ball might warp a rubber sheet, creating a depression. Nearby objects, like planets, follow trajectories in this dented space, which we perceive as orbits. This theory might sound like science fiction, but when applied to the problem of Mercury's orbital precession, it resolves the 7% discrepancy entirely. So what have we learned? Mercury's orbital precession, a long-standing mystery, can be explained by considering the interplay between mass and space. Rather than treating space as a static void, it's a dynamic fabric shaped by the masses within it. This concept, a cornerstone of Einstein's general theory of relativity, not only resolves the issue of Mercury's precession, but also revolutionizes our understanding of gravity and the universe at large. Remember, the universe is not just a stage where celestial bodies perform. It's an active player in the cosmic dance, shaping and being shaped by the masses within it. A simple shift in perspective can solve a mystery that has puzzled scientists for centuries. Now, isn't that an exciting thought? Exciting